Hi, I'm Jay from RS Garage. Today I'm going to walk through the assembly of a RSG1600 short block. This short block includes a Mazworx Stage 2 block, an optional 94mm Brian Cower crank, a CP custom piston, a BME C300 piston pin, and of course the Brian Cower H-beam rod with the optional ARP CA625 Rod Bolt. So as we walk through the assembly, I'll talk a little bit more about the individual parts and how they're on this path of a package of success, and maybe give you some tricks and tips for you to do if you're assembling an engine at home. As far as order of operations, I'm going to shuffle some stuff around and go ahead and measure my bores to make sure they're the right size, and then I'm going to go ahead and file the rings. If you're filing rings for the first time and you put the rings in the cylinder and the ring gaps are bigger than what the specification should be, it's a real good time to stop and measure the bores, because if the machine shop landed you with a thousandths bigger bore than you think you have, then you're going to end up with bigger ring gaps and you could chase your tail a little bit. So verify the bore size. This block was honed with a torque plate on it, so when we measure it without a torque plate, there'll be some variance at the top of the cylinder, but it's an iron block, it doesn't move around a lot, so I can get away with that. So we'll measure the bores and then we'll file rings. So I'm going to take the dial bore gauge that I've set to 3.4055, which is 86.5 millimeters, and I'm just checking for 0 as I move down the bore. First thing I'm going to do is look and make sure that I have all 6 rings and they're all the same part number, because boxing errors can happen from time to time, and we don't want to modify a part that we're not going to be able to use. So all the boxes match, so we can check and see if the rings fit the pistons correctly. So this is the second ring. It's black in color and it's got a Napier hook. The Napier hook is a small ledge on the bottom side of the ring that is used to drag the oil down off the bore as the piston travels back down the bore. It's a really efficient way of cleaning excess oil off the cylinder. When we drop that ring into the piston, it sits down into the land below the surface of the piston. If the ring protrudes up out of the piston like that, you've got the wrong ring set. It needs to drop all the way down to where it's below the surface of the piston. We take a peek at our top ring. It's a nitrated steel top. It drops down below the surface of the piston ringland also. And then we can look at our oil ring kit. Kind of put them in a stack and slide them into the oil ringland. And make sure there's no excessive gap above or below. Then we can take our oil rings and drop them into a cylinder and make sure that there's ring gap. So this isn't super critical. You just want a minimum of 15 thousandths of an inch. These rings cannot be butted. None of the rings can be butted in your engine. That's not how they work. They have to have a gap between the end of each ring. Now it's time to start checking the rings. This block has been washed, but it hasn't been final washed. And I recommend filing rings before you start putting the crankshaft or anything else in the block, because you have an opportunity to put particulate into the engine as you're filing the rings and you haven't cleaned them yet. So I'm going to take this little file here and I'm just going to chase the edge of the ring, because I don't want a sharp edge dragging down my cylinder. I can compress the ring with my fingertips, pop it down below the deck, and square it up with the piston. Once it's squared up with the piston, I can check the as delivered gap. I'm looking for 25 thousandths. So I've got 25 thousandths on my second ring. So I don't have to file the ends of this ring gap, but I do want to chase the bottom of the ring here and the top of the ring. And this is something I've been watching some of you YouTube guys, and there's guys that wear gloves when you're putting an engine together. You're really taking away from the opportunity to feel small edges. Those gloves are thick and they cover up all these nerve endings on your fingertips that you can use to find edges. And an edge, a small edge on a new engine component, can create a large problem in a running engine. So you take your fingernail, kind of run it along the edge of the ring, See if you get it to bite on anything. If you do, just take a small file, real quick. You're not trying to remove much material. You're just knocking the edge off that part. Same with a new piston. If you have a new piston and you're wearing those gloves, you need to be able to take your fingertips and run all around this part, around the valve relief cuts. If there's anything sharp, it's a good time to just a little bit of 1000 grit sandpaper and just knock any real hard edges off of these components, because you don't want it like that in the engine, especially as you get down on the bottom of the piston and the bottom of the bore. This engine block has a stroker notch, and when the CNC machine notches that bottom of the bore, that edge of that tooling is a little bit sharp. So I just take some 1000 grit sandpaper on my fingertip and work around on those edges until they're slick, because I don't want the sharp edge of the bore scraping up the fresh piston. So again, the gloves, this is not a clean game. You're gonna be exposed to chemicals. Your hands are gonna stink for a couple days. Get a manicure next week, it's okay. But when you're working on an engine, like, feel around on your parts, especially if they're new parts, because you wanna be able to detect any edges, and bare fingertips are great for that. As we move to the top ring, same thing. We're not trying to bend this ring up. We're trying to equally compress it, work it down into the bore. You can use our piston to square it. And we have a very, very small gap to start off with here. So this is going to need to be filed. This is really common. It's a file to fit ring. So you're not always going to get lucky like we did on that second ring. We're going to have to cut on this one a bit. We have 12 thousandths now, and we're going to bring that up to 21. Now, I'm only going to file from one side of the ring, and I'm careful to not grind a bunch of heat into this part. It is still quite cool to the touch. If you are filing like a madman and you discolor the end of the ring while you're doing that, you're going to temper that metal, and it's, in my opinion, no good to use. This is not a game of force. It's a game of letting the tool do the work. And if you've discolored the end of that ring at all, I would say it's time to get another ring and be a little bit more gentle. Again, we can feel around on the end of the ring. For what it's worth, the second Napier ring is more likely to roll material off of it as it files, whereas this nitrated ring kind of chips away. So there's not going to be much of an opportunity for extra material that's been rolled over as it's been cut with the file. But with the second ring, you almost always get some of that material rolled over. But just a little bit of file work, very, very gentle. It's a very smooth file, just knocking off that edge of the ring so you don't have anything sharp going on. And that completes cylinder number 6. So I can put them back in a box, label them cylinder number 6, and come back to it when I'm ready for that step. A lot of care has to be taken to make sure that you're filing the end of the ring square. If you look really close, you can see that the ring is not square in the ring filer. So as you move the ring into the ring filer, make sure that you've butted the end of the ring completely square up. That way you're filing evenly. Take small amounts. Remember, you can't put any material back. You've got to file slowly. It's one of those things. Measure twice, cut once. With the ring caps filed, I can put the main caps back on the block and measure the housing bores. So if you watched our last video on the billet main cap installation, the housing bore is the size of the main tunnel. There's a minimum and a maximum to that size. And if you have it too small, you can cause the bearings to buckle. If you have it too large, the bearings won't be properly located in the block. They won't sweat heat properly into the block, and they won't keep shape well. So this is one of the trickiest spots on a 2JZ. If you mess up the align bore and align hone on one of these engines, it won't live well. I put the main caps back on the block. This is using a ARP 8740 stud kit, so it's going to go to 60 foot-pounds. So I'm going to get there in 3 even steps, just work across all 7 mains, and then I can start measuring up the housing bores. So what I've done here is I've set the outside mic to a housing bore dimension, somewhere in the mid to high limit. I'll zero out my inside mic, and then I'll plunge the inside mic into the block, see what the variation is, then I'll come back and I'll adjust it to my outside mic. That way I know what the actual value is in the main tunnel. If you watched the main cap installation video, we talked about the interference fit between the cap and the block. And as you can see, the caps kind of snap down into the registers. So there is interference fit. That's why you have to bolt them down in there gently. But what you're seeing is the register to main cap, the block is smaller than the cap. So that helps locate the cap in operation. The bearing on the right is a out-of-the-box king-coated bearing. The bearing on the left is also a king-coated bearing, but I've used some Scotch-Brite and cleaned the back of the bearing. So the back of the bearing doesn't have a coating, it's just bare metal. And that's just so the heat can transfer out of the bearing back into the main saddle easier. When you pull the main cap down into the saddle, you want to do it evenly. And I've got a clean bearing back with some light oil on it, and as I squeeze the caps together, the bearing is located in the block. There are tabs on the bearing to hold the bearing in place during installation, but the actual force between the upper bearing and lower bearing meeting at the parting line is what holds the bearing in place. For those of you that haven't seen me do this before, this is the size of the crankshaft main. So I use my outside mic, put it on the crankshaft, and understand what size the diameter of the main journal is. Then I take my inside mic and I zero it in the outside mic. Now when I put this inside mic in the block with the bearing cap torqued in place, I can have the bearing clearance, which in this case with a mixed set of H and HX bearings is right at 3 thousandths, 2.7, 2.8 on this main journal. So I've installed all the caps because if it's within the range that I desire, I can go ahead and torque the rest of the caps down and check it. If it was too big or too small, I just pop a cap off, pop the caps off and switch them to H or HX as a full set. But I'm okay with that number, so I'm going to move to the second cap and see if it repeats well. As you can see, you have 2.5 thousandths of vertical oil clearance, and if we move over closer to the parting line, that number opens way up, so there's 4 thousandths there. So as you notice, you had 2.5 thousandths of vertical oil clearance, but then 4 thousandths out here. In this area near the parting line of the bearing, is got more bearing clearance because the bearing is not perfectly round. The housing bore is perfectly round, but there's a certain amount of eccentricity to the bearing, and that's allowing oil to sit in this area of the bearing to be picked up and travel around the crankshaft. So it's kind of like a reservoir, just like this trough is on the upper bearing in the main. During the process of measuring the mains, I ended up having a split set of bearings installed into the block. So half a set of the bearings are standard size and half the set of the bearings are HX. And I'll put the HXs all in the lowers and the standards in the uppers. Measured the clearance, I'm happy with those, so now I can move to the rods. So I need to measure the crankshaft, make sure all the journals are within specification, and whether or not they're on the low limit or the high limit, because that'll help me select the rod bearings I need to get the vertical oil clearance on the connecting rods. So I need to measure through the housing bores on the connecting rods, just like we did on the block. Then I can measure my crankshaft. Then I can put some bearings in and see what we have for vertical oil clearance. Just like we did on the main housing bore, we're going to set the outside mic to the target size of the large end of the connecting rod. That's the housing bore. We zero the inside mic in the outside mic, and now when we plunge the inside mic into the torqued connecting rod, we'll know what that housing bore size is, and then we can make sure that all of the housing bores are not only within specification, but that they're all matched within reason. So a couple of 10,000ths of an inch is not going to hurt you here, but the main thing is there's a low side and a high side to the housing bore, just like there was on the main bearing. This is a Toyota journal crank, so we should have 2166 as our journal size. And we are at size and we're round. So this rod checks out on the big end sizing. So we need to mark it checked and we can move to the next rod. This is one of the things that when you buy a quality part, it goes a long way. The sizing on these BC rods from rod to rod, set to set, really excellent job by the men that create them on tolerances. If you save a little bit of money on the front end by buying a lower cost set of connecting rods, and you have to spend money to have them resized, you're not really saving any money in the long run. So you're always going to check pin fit, and while those numbers are also on target with a set of BC rods, it's something you're always going to check or pay to check. But you don't want to be paying to resize a brand new set of rods. It's just a waste of time and money, and you can avoid it by buying a quality part. A couple things that you may or may not know: the bearing tangs are always going to face each other. So when you put the rod together, it's tang to tang. You also have these dowels that are located in the cap in the main body of the rod. You don't want to distort those. So when you bolt your rod together, you don't want to tighten one side down and leave the other side loose. You're going to pull the cap onto the body of the rod in equal turns to keep distortion at that dowel at a minimum. We've measured the large end of the connecting rods, and we have 4 10,000ths of an inch between our largest rod and our smallest rod, so less than half a thousandth of an inch. Now, the housing bore does influence the bearing clearance, but you want to be between the min and the max of your housing bore. You're chasing very small numbers at this point, and your engine won't live or die because of less than half a thousandth of an inch. You know, you generally are going to aim towards more reasonable goals when you put an engine together, because there's 12 different bearings that make up your rod bearings. And if they're all within specification and they all have vertical oil clearance and all the housing bores are within the min and the max, and you don't damage anything putting it together, the engine is not going to have a measurable difference in its life because there was 0.0001 of a variance when you go across a set of parts. Those variances are too small to really chase, especially you start talking about different temperatures. So housing bores are within spec. We're going to go ahead and start sliding some rod bearings in, measure our vertical oil clearance, and we can move to the next step. When you watch me put the bearing into the rod or into the main, I like to slide them around a little bit just to make sure the back of the bearing has the ability to move inside of the shell during assembly. Once the rod is bolted to the cap or the cap is bolted to the rod, none of that stuff's moving, but it's got to be able to float to get to its final location. Now that our rods are all checked, we can take the main caps back off the block, put some light oil, like ATF, on the bearings, put our thrust bearing in. We're going to check in play, and we're also just going to feel how the crank spins when it's in the engine. And this is why I'm going to use thin oil. When you use thick oil or assembly lube, that's a different purpose base, and you won't get a very good feel. If you put grease on the bearings and then turn the crank's not going to feel very smooth. But the thin oil, it loans itself to giving you a good indication of whether or not there's any friction or binding, which there really shouldn't be, and it's not. I've never run into a situation that had a weird feel to it unless the crank was bent. And this is also a good time if you're dealing with a used crankshaft to check and see if it's straight. But you got to check the thrust clearance anyway, so you might as well give the crank a spin with some thin oil so you can get a feel for it. Now the crankshaft isn't exactly light, so depending on how strong you are, it's always a good idea to take the main studs out of the block so you don't run the risk of brushing one of these precious crank journals up against the sharp threads of a stud. So it just takes an extra minute, get the studs out of the way, you drop the crank in. I've dropped the crank in with the counterweight around the thrust flat, so it's not in my way as I slide the thrust bearings in. So that'll be pretty simple. If you had the counterweight up, and you have to kind of fish the thrusts around, so that'll make it pretty easy for me. We understand that the caps are located side to side by the registers, but there's nothing locating the cap front to back. And there's not a lot of room on 1, 2, 3, 5, 6, 7 for them to be in the wrong place. You tighten the cap down, it locates on the hardware, it locates on the registers, you've checked your oil clearance, you torque it in place, it's good to move on. Thrust washer is a bit different. You want your thrust washer to be perfectly lined up on the face of it, because every time you push the clutch or your torque converter balloons a little bit, you've got any force on the back side of that crankshaft or front side of the crankshaft, depending on the clutch configuration, you want to make sure that you have 360 degrees of bearing surface available to help mitigate that load. So you're going to knock the crankshaft back and forth a couple times, which is going to locate the thrust face of the crank against the thrust bearings and locate that cap where the cap, from the cap to block thrust face, is in perfect alignment. So you just give it some wax back and forth, and then I'm going to go ahead and put it back and put not a lot of pressure, but I put a little bit of pressure on it between the block and the crank to just push the crank backwards. And then I can torque the number 4 main cap and check my thrust clearance. And at the same time, like I mentioned before, we're just going to check and see how the crank spins. We verified the thrust clearance. Our crankshaft turns beautifully. There's one more thing we can do before we take the engine back apart for final wash, and that is check the location of the oil pump in relation to the oil pump drive gear. So I'm going to grab the oil pump that's going to go on the engine. There's dowels in the face of the block. I'll bolt it in place, and I have a fixture tool to just check and make sure that the housing is in alignment with the crankshaft. So this is a simple tool that we whipped up to see that the oil pump is in the correct location. So I slide this into the oil pump. So this is going to mimic the front seal, and it doesn't have any bind on the crankshaft. So I can turn these two independently, and there's very small clearance between the two parts. So if the crankshaft was not in the right location because the block had been aggressively line bored, or there's a problem machining with the pump housing, I know now before I put the pump on for the last time that I've got a problem that I need to solve it. So it's just a simple go, no go test that I've incorporated as housing machining has changed and all the blocks are never exactly the same. With the crankshaft back out of the block, I can do my final wash on the block. I'm going to rewash the bearings, rewash the caps, get everything clean, and then get to the fun part, which is putting it together. With the block wash, I need to go through and wipe the bores down again with some ATF on a lint-free towel. So I'll just keep wiping and wiping and wiping the bores until the towel comes out clean. And that way I know that in those valleys of all that crosshatch and the honing is clean of any debris or oil or any nonsense that's gone on. And even though you can take a dry towel and wipe the bore and it will stay clean, once you wet that towel up with some ATF and you start scrubbing, you'll see that there's still things in those small crevice tiles of the bore that they're not going to come out otherwise. So this is the practice. Just take your time. It's going to cost you 20 minutes, but you can get all those bores perfectly clean and ready for the new pistons and rings. these main studs are ARP. They're made from an 8740 material. ARP only manufactures from the top 2 grades of 8740. 8740 comes in multiple grades of material. And this material in this size will provide over 12,500 pounds of clamp load holding the main cap in place. And for most engines in the 1,000, 11, 1,200 horsepower range, that's fine. And after that, you can move to a 625 stud, which we offer, which will put almost 40% more clamp load to stabilize that cap in place. Now I'm not tightening the studs into the block. They're just in there just before they meet. So there's tight, and I just back them off a little bit so they're just floating, because I don't want any tension on that last thread of the stud and the first thread of the block. I want them to have a pretty neutral relationship. If you're working with an older engine, like a engine that has a coarse thread, like a 1/2 inch 13 thread pitch bolt, well, that relationship can actually cause the stud to be at a slight angle during installation, and then you're not going to be pulling on that stud evenly. It's going to be cocked off a bit, which you don't want that. You want things to be pretty neutral as you tighten them up. I'm installing this main stud kit with ARP's Ultra Torque Lube. The Ultra Torque Lube is not the slipperiest stuff on the planet. If you had essentially put together packs of ball bearings between the thread would act as a spring. You'd tighten the fastener down, and then it would be able to unwind itself. So there's a certain amount of friction that the lubricant needs to present. So it's not just an anti-friction, it's more so an attempt in consistency, because as the fastener torque changes and friction changes, the clamp load changes. And ideally, you'd have the same clamp load on all of the fasteners. That's why when you watch those big OEM tools that have 4 or 6 or 10 heads on them, and they tighten all the fasteners down at once, that's in an effort to minimize distortion across the part. Not as much of a problem on a main cap, but a pretty decent sized problem when you start talking about bed plates and you start talking about head gaskets, which anyone that's watching this is probably aware that the head gasket area is under a lot of pressure, and you don't want to get into leaking or blown head gaskets, because you've got a big mess on your hands now. So using the proper lube and torquing the fasteners down correctly is your responsibility and your defense against having problems. But there's also some plan behind this lubricant's ability to stay put, because if you just put a lubricant in place that was just strictly for assembly, then what would be there to protect the fastener threads during disassembly? So there are some lubricants on the market that are they're very slippery, but they don't stay put with heat. So then when you go to take the engine apart, you could damage fasteners coming apart. So this is not just an assembly type lube. This is a surface lube for the threads on the fasteners, especially engineered. It's what you should be using. When you start talking about assembly lube, like this is an assembly lube. This thick, sticky oil's job is to stay put while the end user remembers that he forgot to plug in the cam sensor and the engine's cranking and cranking and cranking and it's not starting. And because it hasn't primed itself, it doesn't have any oil pressure, and you want something thick and sticky to stay in place to protect the bearings until the engine fires. So they're very different, and you'll end up using quite a few different lubricants and a different set of oils when you put an engine together, because everything kind of has its place. But as far as on threads, just stick to the ARP Ultra Torque. It's your best bet, and it will present repeatable results and less torque scatter as you install the different fasteners on your engine. Now when we go back through and we turn the crank with that thick assembly lube, you can tell it's sticky, and it's just there to protect you in startup. That's its whole job. So if you went to Toyota and you saw how they assembled engines, it would just be with oil, and they'd get to the end of the assembly line, they'd fire the car off, and away you go. But things happen, and assembly lube is going to be there to protect you in case you have an incident. Now with this engine, the size of the pickup, the cranking speed of the engine, I don't recommend that you crank the engine to prime the oil pump. I recommend that you make sure that you don't have any air leaks, any gross air leaks, that the engine isn't going to flare up in a lot of RPM when you start it. But you're just going to get the engine fired, let it idle at a low speed for 3, 4, 5 seconds until it builds oil pressure, and then get the engine speed up so you can get oil slinging around inside the engine and get those new parts to start to break in. But I always do the spin test with the ATF because I want to feel the crank. I want to see how it feels. And after you do this for a while, you'll get used to what normal feels like and what something that's abnormal feels like. But if you had the whole crank covered in thick lube or grease and you're turning it, you have no real feel of what's going on. It goes back to kind of like working with gloves. You know, you want to be able to understand what's happening with the parts the best you can, because all of these are all gorgeous parts. They've never worked together before, and you could catch something during assembly. And that's why you want to kind of get a feel for things, work slow, pay attention, and have a good outcome. Now it's time to put the pistons and rods together. Now, if you were paying attention, you notice that I measured the bores, but I did not measure piston to wall clearance. And that's because before I sent these pistons out to be coated, I measured the piston to wall clearance, and it was around 4.5 thousandths. And I had line to line apply 2 thousandths of their abradable coating, which I think is pretty neat stuff. And it's going to wear that coating away as needed while maintaining a perfect shape of the piston, because the piston doesn't grow evenly with heat. And because it doesn't grow evenly with heat and stress, the skirts don't stay exactly the same shape. And that abradable coating will wear as needed. So if you run the abradable coating and then you take the engine back apart, you can kind of see how the piston changes shape in operation. It's really neat stuff. It also helps keep oil around, and oil on the bores, the right amount of oil on the bores is your friend, especially if you're using an alcohol-based fuel like ethanol or methanol, where it has the tendency to wash the bores. So pretty neat little add-on for this engine. This engine is going to be in a drifting car, which is going to be a pretty wicked combination because 94mm crank, 10-to-1 compression, nice rods, nice bearings. This is one of my favorite JZ platforms because it makes a lot of power and it revs up good. You know, when I had my version of this in my own car, I made almost 1,500 wheel with it and went to half-mile events and drag raced it and had a really good time. It averages well. The additional stroke is nice. There's some guys that they may not be, they may get caught up in the math of a stroker engine because the rod stroke ratios get a little hairy and the rod angles get a little hairy, but there's no denying how well they run and how well they perform. So this will be a pretty neat car. I don't know if this car is getting a VVTi head or not, but if you pair a stroker crank with a VVTi head, you really get an engine that has a ton of average power and still revs up well. You know, you want to get most of your action done before 8,500 because stock oil pumps not doing you much good past that or even there. And while this engine will have a modified stock oil pump, but the restrictions of the factory oil system, they kind of remain, they haunt you. So unless you have a dry sump, you don't want to be revving the engine much past that. And most guys have synchronized transmissions, so your synchronizers also don't really love being north of 8,500. So this will be a good engine, and they'll probably set the limiter to 83, 8,500 RPM, and it'll be pretty righteous. Now after I filed the rings, I blew them off with just clean, dry air. And then I'm going to give them a wipe with some ATF before I put them on the pistons. So this will give an opportunity to get some kind of lubricant all over the ring. And you don't want to cover the ring in oil. The ring never is saturated in oil. It works in an environment that it has access to oil, but it's not covered in oil during engine operation, and nor would you want it to be, because the rings can't clear that much oil off the cylinder. So you just want them lubricated for startup. So I'm using a light oil like ATF again to make sure that there's some lubrication present on the ring as it goes into action. I'm going to wipe the bores with some non-detergent oil just so there's some lubrication present, and it also helps keep corrosion at bay, because I don't know when this engine is going to be started, so you want to make sure that you have your critical surfaces lubricated so you don't get into rust, especially in the bores. The bores are the most sensitive part of the engine when it comes to corrosion. So give them a quick wipe with some oil, and then I can load some pistons in. I'm also going to scrub the skirts with some motor oil just to make sure that they have some lubrication present down in that coating so the coating isn't dry. One of the things this coating does force you to do is break it in. So when this engine is started, he'll have to run it just like you'd run a flat top at KMN, which you have to deal with that on this engine anyway. So you start the engine up, run it at low load, steady RPM, small variances, and load, and then you can bring in more load, change the oil, and then kind of get to it. But this piston coating will wear in over time. It adds time to the job and it adds cost to the job, but the final result is what I would argue better. Ford actually used some of these coatings as far back as the early 90s. And if you're a Ford tech, you can correct me if I'm wrong, but the early Ford 4.6 engines had an abradable coating, and they had 0 piston to wall clearance because the coating was taking up all that space. Early in, when I was filing rings, I talked about deburring the edges of the rings, and now's your time to kind of your last check. So as you slide these piston rings around in the ring lands, there should be no sticky point. It should be free, free, free as it slides around in the ring land. Isn't that tool a breeze? Come on. Have you used that tool before? Just making it easy. If you haven't noticed, there's a bunch of pretty O-ring purple plugs on this engine block, and that's one of the Mazworx signatures. So the main galley balls are pulled out and they're tapped with a 17mm thread with an O-ring plug for easy service, easy cleaning. And you also get, instead of a knock-in freeze plug, you get these pretty screw-in freeze plugs that are also serviceable. And if you need to add coolant in the side of the engine, you've got a screw-in plug to access that in case you're changing how the coolant is flowing through the engine like we do out at Bonneville. I hope you've enjoyed the video. If you have any questions regarding your 2JZ build or you're looking for any other go fast bits, please keep us in mind and feel free to reach out. Thanks, and I'll see you next time.